To section 4.1, basic graphs. The sine and cosine functions are fundamental trigonometric functions that model periodic behavior, such as sound waves, tides, and circular motion. Their graphs are known as sinusoids and can be constructed using the unit circle as a reference. To graph y equals sine x and y equals cosine x, we use key points from the unit circle which correspond to special angles or values, special angle values. Sine values represent the y-coordinates of points on the unit circle, and cosine values represent the x-coordinates of points on the unit circle. So let's fill in our unit circle with the information we already know. So let's first start off with the positive trig values per quadrant. So in quadrant 1, we know that all trig functions are positive. In quadrant 2, we know sine is positive, therefore its opposite, cosecant, is also positive. In quadrant 3, we know tan is positive and its opposite, cotangent, is also positive. And in quadrant 4, we know cosine is positive and its opposite, secant, is also positive. According to the information that we just read, we know the sine of theta is going to equal the y-coordinate. So the y-coordinate is the value for the sine of our angle. For cosine theta, that will equal x, because the cosine values represent the x-coordinates of points on the unit circle. Now tangent is going to be sine divided by cosine, so that's going to be y divided by x. So if we wanted to find the tangent of a specific angle, we'll just take the y-coordinate and divide it by the x-coordinate. So since we know sine, cosine, tangent, we can then identify cosecant, secant, and cotangent. So cosecant would be the reciprocal, so that's going to be 1 over y. Secant would be the reciprocal of cosine, so that would be 1 over x. And cotangent would be the reciprocal of tan, so that would be x divided by y. Okay. So now that we have all of this key information, let's complete our unit circle. So starting in quadrant 1, with a radius of 1, the cosine of 0 degrees, or 2 pi, is going to be 1, and the sine will be 0. For 30 degrees, the cosine will be square root 3 over 2, and the sine would be 1/2. For 45 degrees, the cosine and sine are the same value, square root 2 over 2. 60 degrees, cosine is 1/2, sine is square root 3 over 2. For 90 degrees, cosine is 0, sine is 1. All right, and so now we're in quadrant 2, and we know in quadrant 2, all of the sine is positive, which means all of the y-coordinates are positive. And we'll know here, since we're in the second quadrant, that the x-coordinate, so our cosines, will be negative. So for 120 degrees, this has a reference angle of 60 degrees. So the 60 degree points were 1/2 and square root 3 over 2. But we know that the cosine, the x-coordinate, is going to be negative. For 135, this has a reference angle of 45, so the 45 degree points are square root 2 over 2. square root 2 over 2. Cosine is negative. 150 degrees has a reference angle of 30, and the points for the 30-degree angle are square root 3 over 2 and 1/2. Cosine is negative. All right, and then 180 degrees, the cosine's -1, the sine is 0. So now we're in quadrant 3. Okay. So in quadrant 3, the tangent is positive. So both cosine and sine are both going to be negative. So for 210 degrees, all right, the reference angle is 30. So we'll use the points for 30 degrees, which is square root 3 over 2 and 1/2. And then both are negative. 225 degrees, the reference angle is 45. So that would be square root 2 over 2, square root 2 over 2. Both are negative. 240 degrees, the reference angle is 60, so that would be 1/2, and the square root 3 over 2, so that's negative, negative. 270 degrees, so the cosine would be 0, sine would be -1. All right, now we're in quadrant 4, last quadrant. In quadrant 4, we know cosine is positive, so that means all the sine values are going to be negative, and we know sine is the y-coordinate. So 300 degrees has a reference angle of 60, and the point for 60 degrees is 1/2 and square root 3 over 2. But we know in quadrant 4 only cosine is positive, so that means our y-coordinate is negative. All right, 315 has a reference angle of 45, so the point for 45 is square root 2 over 2, square root 2 over 2, and then our y-coordinate is negative. And then 330 degrees has a reference angle of 30 degrees. The point for 30 degrees is square root 3 over 2, 1/2, and this quadrant, the y-coordinate is negative. So we have now just completed the unit circle, which we will be using to help graph our trigonometric functions. Functions that repeat at regular intervals are called periodic functions. Period is the length of one complete cycle. It can start at any point on the graph. In symbols, if p is the smallest positive number for which f of x plus p equals f of x for all x, then we say the period of f of x is p. The amplitude is half the distance between the minimum and maximum values. In symbols, it can be defined as a equals 1/2 times the absolute value capital M minus m, or maximum minus minimum. All right, let's go through our first objective. Graph sine and cosine functions. So let's first start off with the sine function. So y equals, if it was written in function form, f of x sine x. Okay, so we can use the unit circle or this table here on the left-hand side to help us graph the sine function. Okay, note that the first column here are our x values, so you can think of those as theta. When we substitute theta into the function, we then get our y. Once we have the y values, we then have ordered pairs. So we're going to graph each ordered pair and then connect it with a smooth curve. Okay. So my x values go in increments of pi over 4, and as you see here on my graph, I also increase by pi over 4. So my first point is going to be 0, 0. So let's plot that point. That'll be 0, 0. Okay. Let me use a highlighter, so it's like bolder for you. There we go. Okay. Next point at pi over 4, we have pi over 4 and 0.7. So that would be like somewhere here. And then we have pi over 2, 1. And then we have 3 pi over 4, 0.7. And then we have pi, 0. Then we have 5 pi over 4, negative 0.7. Then we have 3 pi over 2, negative 1. Then 7 pi over 4, negative 0.7. And then we have 2 pi, 0. Okay. And so now we can connect those dots. Oh, my 2 pi over, my point disappeared. Let's replot that. There we go. Okay. All right. So here you can see that we have one complete cycle. All right. We started at 0, went through the x-axis, and then came back to 0. So this is one complete cycle. Okay. If we were to continue this pattern, you'd see that it would be repeating, we would be repeating the similar y values. So we can extend the graph to the left of x equals 0, since one complete cycle here is 2 pi. All right, one complete cycle here is 2 pi. We know that the sine graph repeats itself every 2 pi units. And we can use the calculator to assist us with the plotting of these points or the unit circle. So let's plot these points to the left of 0. So we would have negative 0.7, negative 1, negative 0.7, 0, 0.7, 1, 0.7, and then back to 0. So if we were to connect those dots, let's put an arrow over here because it continues on. We have the parent function of our sine graph. Excellent. All right, let's now state some descriptors of our sine graph. Well, the domain is going to be from negative infinity to infinity. The range is going to be from negative 1 to 1. The x-intercept, so this is where the graph crosses the x-axis, is going to be n times pi, where n is an element of the integers. Okay, so whenever you see the symbol, it means integer. Okay. The y-intercept is going to be 0, so that's where the graph crosses the y-axis. There are no asymptotes in the sine graph. The amplitude is going to be half the distance between the maximum minus the minimum. So that would be 1/2 times the absolute value of 2, which would be 1. So the amplitude will be 1. The period, we know, is 2 pi. Okay, so those are the descriptors of the sine graph. All right, let's do the next one, cosine. So y, if it was a function, f of x equals cosine x. Okay. We have our theta, so our x values. We then substitute it into the cosine function to then get our ordered pairs, which we are now going to graph. So for the cosine graph, it starts at 0, 1, whereas the sine graph started on the origin. Then we go down to 1 divided by square root 2, or square root 2 over 2. Square root 2 over 2 is approximately 0.7. Then we have pi over 2, 0. Then we have negative 0.7. Then we have negative 1. Then we have negative 0.7. Then we have 0. Then we have 0.7. And then we have 1. And so now we can connect these dots. Okay, so similar to the sine graph, we know that this right here is going to be one complete cycle. So our period is going to be 2 pi. So that means cosine repeats itself every 2 pi. So we can extend this graph to the left side of x equals 0, following a similar pattern. Okay. So going to negative pi over 4, we'll have 0.7, then 0, then negative 0.7, then negative 1, then negative 0.7, then 0, then 0.7, and then 1. Okay, connecting the dots. All right, and we have our cosine graph. So the descriptors, or properties, I guess you could say, of cosine. The domain is negative infinity to infinity. The range is negative 1 to 1. The x-intercepts are going to be pi divided by 2 plus n times pi, where n is an element of the integers. Our y-intercept is going to be 1. Cosine does not have any asymptotes. The amplitude is going to be half the distance between the maximum minus the minimum. So that's 1/2 times the absolute value of 2, which is 1. And the period is going to be 2 pi. All right, that's objective 1. Okay, so for objective 2, we are now going to graph the tangent function. Okay, so for our parent function, y equals, if it were a function, f of x equals tan x. Okay, we have our x values here, and then we have our y's. Okay, note that at pi over 2 and 3 pi over 2, our y value is undefined. Therefore, there is no y value that exists. So we are going to place dashed lines to signify that our y is undefined at that x value. So pi over 2 is right here. And then 3 pi over 2. Okay, so we know now that we have asymptotes at these two x values. Okay, so let's plot some points. So we have 0, 0, 0, 0, then we have 1, then we have pi over 3, which is roughly in there, in between pi over 4 and pi over 2, which is 1.7. Okay. Then we have undefined, then we have negative 1.7. So that would be 1.7, so roughly in here. Then we have negative 1, then we have 0, then we have 1, then we have 1.7, then we have undefined, then we have negative 1.7, negative 1, and 0. Okay, so let's connect our dots. So our graph would look something like this. So this is the tan graph. All right. We see here that a complete cycle is the same as our period, which is just pi. All right. As a length of pi. We can now extend this graph to the left-hand side following a similar pattern. So let's do that. So we have negative 1, negative 1.7, and then we have an asymptote. So it's approaching pi over 2. So it will be approaching negative pi over 2. All right, and then we start up again here at positive 1.7, then negative 1, or sorry, not negative 1, positive 1, 0, negative 1, and then negative 1.7, and then we have an asymptote. And we start up again, positive 1.7, 1, 0. Okay, and then we can connect our dots. So let's finish this one here. Oop, there we go. This one. And then this one. Awesome. Okay, so that is our tangent graph. All right, our properties of our tangent graph. So we have asymptotes. So our domain is going to be an element of the real numbers, but our x cannot equal pi over 2 plus n times pi, where n is an element of the integers. The range is from negative infinity to infinity. The x-intercepts are n times pi, where n is an element of the integers. The y-intercept is 0. The asymptotes are going to be x equals n over 2 plus n times pi, where n is an element of the integers. The amplitude is undefined, and that's because there is no minimum and maximum values, and the period is going to be pi. Awesome. Okay. Next objective is to graph reciprocal trigonometric functions. So we are going to graph the reciprocal trigonometric functions of sine, cosine, and tangent. All right, starting off with cosecant. So we have y equals f of x, which equals cosecant x. We can use the values of sine to help us graph the cosecant graph by taking the reciprocal of all of the y values. So if we have 1, if we have 1 as a y value for sine, the cosecant would be 1. If we have 1/2, the cosecant would be 2. If we have 1/4, the cosecant would be 4. If we have 0, the cosecant would actually be undefined, because 1 over 0 is undefined. It doesn't exist, and so on and so forth. Okay? So, wherever we have 0 for sine, we know we're going to have an asymptote. So, according to this table, sine is 0 at 0 radians or degrees, at pi, and at 2 pi. So that means we have asymptotes on the y-axis. At pi, and at 2 pi. Okay, so let's graph. So we have 0.7, so if we were to take the reciprocal of that, we would have roughly 1.4. So pi over 4 is roughly 1.4, so almost 1.5. Let's put that right there. Okay. And then we have 1, the reciprocal of 1 is 1, and then we'll have the reciprocal of 0.7, again, almost 1.5, and then we have 0. And then we move over to our next one, 5 pi over 4, so that would be negative the reciprocal, which would be here. And then we'd have negative 1, negative 1.4. So let's connect those dots. So we know the period for sine is 2 pi. So the period for cosecant would also be 2 pi. So 1 complete cycle. So we can continue this process on the left-hand side of x equals 0. So let's draw our asymptotes. At negative pi and 2 pi. And then continue the pattern. So we would have negative 1.4, negative 1, negative 1.4, and then positive 1.4, 1, and 1.4. And we can now connect the dots. All right, and that is the cosecant graph. And if we were to draw our sine graph, we'd see that the cosecant is actually the opposite, or the reciprocal of the sine. Oh, what's happening? All right, let's figure out what's happening. There we go. Let's erase all that. There we go. Much better. There we go. Okay, awesome. Let's do the next one. Oh, before we do that, we gotta do the properties. Almost forgot. All right, the domain is going to be all x that are an element of the real numbers, except for when x equals n times pi, where n is an element of the integers. The range is going to be from negative infinity to negative 1, union negative 1 to infinity. There are no x-intercepts. There are no y-intercepts. The asymptotes is going to be x equals n times pi, where n is an element of the integers. The amplitude is undefined. There's no maximum value. And the period we know is 2 pi. Awesome. All right, now let's do secant. Secant is the reciprocal of cosine, which I just wrote, but I meant to write secant. So we can use the values of cosine to help us graph our secant graph. Similarly, wherever we see 0 as a value for cosine, we know we're going to have an asymptote. So let's plot those first. So we have 0 at pi over 2. And we have 0 at 3 pi over 2. Okay. So let's plot. So we have 1 for cosine, so the reciprocal is 1. Okay. Then we have square root 2 over 2, which is 1.4, almost 1.5. Then we have an asymptote. Then we have negative 1.5 or 1.4. Then we have negative 1 and then negative 1.4. Then we have an asymptote. Then we will have positive 1.4 and then negative 1. So let's connect these dots. It's very similar to cosecant. Oh, I put this on 0. I should have put this on 1. There we go. All right. So our period here is still 2 pi. Okay. So we can extend this to the left-hand side of our graph. So let's add our asymptotes, which will be negative pi over 2 and negative 3 pi over 2. Okay. Then we can plot our points. So negative pi over 4 would be positive 1.4, and we would have asymptote. Then we would have negative 1.4, negative 1, negative 1.4, asymptote, positive 1.4, and negative 1. Or sorry, positive 1. Positive 1. We're above the x-axis. So let's connect our points. Approaching the asymptote. All right. And that is our secant graph. Note you can see the cosine graph in the reciprocal secant graph. Okay. Awesome. All right, let's look at some properties. So the domain is going to be the elements, or all the x element. Let me rephrase. The domain is going to consist of all x that are an element of the real numbers, except for when x equals pi over 2 plus n times pi, where n is an element of the integers. The range will be from negative infinity to negative 1, union 1 to infinity. The x-intercepts, there are none. Y-intercepts, 1, crosses the graph at 1 on the y-axis. The asymptotes are going to be x equals pi over 2 plus n times pi, where n is an element of the integers. The period is going to be undefined. There is no maximum value. Sorry, the amplitude. The period is 2 pi. Read too quickly there. The amplitude is undefined because there's no maximum, and our period is 2 pi. Awesome. Okay, let's do our last reciprocal function, which is y equals f of x, which equals cotangent x. So we are going to use the values of tan to help us graph this. All right. We see here that wherever we have a 0, we know will be undefined, whereas wherever will be undefined will actually be 1, because we know the tan is our y over x, so our sine over cosine. And for sine over cosine, the only reason why we have undefined for tan is because we have 1 over 0. So if we were to take the reciprocal of that, 0 over 1, we would just get 0. So when we're trying to plot cotangent, wherever we see 0 for tan, it'll then be undefined. And wherever we see undefined, it's going to be 0. All right. Let's erase this scribble here. Okay. So let's graph our asymptote. So remember, wherever there is a 0, we're going to have an asymptote. So we have a 0 at 0, so we'll have a 0 on the y-axis. We have a 0 at pi, so pi is going to have an asymptote, and a 0 at 2 pi. Okay, so now we can plot, start to plot. All right, so we have one for pi over 4, and then we have pi over 3, which would be in between pi over 4 and pi over 2. But let's stick to the main increments of pi over 4. So the next one would be pi over 2, which is undefined, which we know would be 0. Then 3 pi over 4, which would be negative 1. And then we have an asymptote, and then we would have 1 again, and then 0, and then negative 1. Okay, so let's graph. Okay, that's 1. Let's go with the other one. They're fun to draw. Alrighty. Okay. So we see here that our period is pi. Okay, so that's one complete cycle. So we can now extend the graph to the left-hand side. So we know we'll have an asymptote at pi, or negative pi, and negative 2 pi. Okay, and then we'll start at negative 1 for negative pi over 4, 0, 1, asymptote, negative 1, 0, 1, asymptote. Then we can graph or connect our dots. And there we go. Awesome. Yay. All right, let's list our properties. So the domain for cotangent is going to consist of x values and element that are elements of the real, but we can't have x values that equal n times pi, where n is an element of the integers. The range is going to be from negative infinity to infinity. The x-intercepts is going to be pi divided by 2 plus n times pi, where n is an element of the integers. The y-intercepts are none. The asymptotes are going to be x equals n times pi, where n is an element of the integers. The amplitude is undefined. There is no minimum or maximum value. And the period is pi. All right. That concludes objective number 3.